Welcome to Module 11 on telecommunications. We're going to just have an overview discussion here on the different types of telecommunication systems that are used in power systems. And it's interesting, as time goes on, power systems are becoming more and more dependent on telecommunications. And you're going to see some of the different types of systems that are being used by the power industry in order to provide the necessary telecommunications for things like system control and SCADA, data communications for computers and internet, talk about call centers, and even protective relaying, and to be able to do transfer tripping and those types of things. The need for telecommunications in the power system has never been greater. Now with smart grid, it's even more reason for telecommunications, and reliable telecommunications is essential. So let's talk about telecommunications for a little bit. Okay, so the objectives of this module are: describe the main types of telecommunication systems used in the electric power industry, describe how the various telecommunication systems communicate data between both ends, and I guess that's basically the two main points here. All right, let's talk about power line carrier. Power line carrier is a very interesting means of communications. It's been around for a long, long time. It's very basic, and it doesn't have great bells and whistles or super capabilities as we have in more modern communications like fiber optics and microwave. But power line carrier is very reliable. It's something that's been around for a long time. Now, what we have here is a substation on both ends, and we have circuit breakers. So here's our power line, just a basic regular power line. It's a one-line diagram of the three-phase power line. But there's a coil in here, and that coil is referred to as a line trap, a wave trap, a choke, okay? And this coil is in series with the power line, and there's another one on this end. Then we have a capacitor here connecting the radio, and another capacitor connecting the radio over here. And what happens is what we talked about earlier in the electronics and the DC and the AC, and mainly in the AC, at low frequencies, an inductor is a short circuit. At high frequencies, the inductor is an open circuit. Remember that conversation. So over here, at low frequency, 60 hertz, the inductor looks like a short circuit. So our 60 hertz power goes right through inductors, no problem. Goes through inductors. We use transformers in our system. We have reactors. I mean, we use coils all the time. Not an issue with power, okay? Low frequency power, not an issue. But capacitors, remember, at low frequencies look like open circuits. So no energy from the power is going into the radio, because those look like open circuits at low frequency, if you remember the formula for capacitive reactance. But at high frequencies, capacitors look like short circuits. So capacitors look like short circuits for 150,000 hertz to 300,000 kilohertz. So 150 kilohertz to 300 kilohertz, capacitors look like short circuits. Inductors look like open circuits. So your radio frequency energy goes through the capacitor, is blocked by the coil, travels down, propagates down the transmission line, blocked by the line trap at the other end, and goes into the radio at the far end. So we have radio high frequency communications on power line carrier, usually one conductor of the three-phase line, typically the center conductor, and we have line traps. Now the picture on the far right shows a coupling capacitor here, and it's jumpered in front of the line trap. You can see the line trap, and that's the coil. There's the coupling capacitor, and then there's a coax going to the radio. So power line carrier, it's good for transfer trips, sending a signal to the far end and tripping a breaker. You can operate voice communications, but it's pretty low quality, and if there's snow coming on the line, you get a lot of static and a lot of noise, and it almost sounds like low-speed data. So when it comes to data communications, very low speed. You know, 300 to 1200 baud. I mean, we're talking really, really slow. But it's enough to send a transfer trip or some kind of information. And you might be able to multiplex up to, you know, 12 channels at the same time. Okay, so that's power line carrier. It's reliable. It's been in service for a long time. And you don't get too many people getting in the way of high voltage communications, you know, with power line carrier. Okay, the next slide has to do with microwave communications. Okay, our systems use quite a few microwave communication systems. Okay, and the idea here is a microwave radio would send high frequency radio energy, and the higher the frequency, the smaller the wavelength, the smaller the antenna. When you think of your cell phone, the antenna is so small because the frequency is so high compared to an AM radio in your car. The frequency is much lower. We're talking, you know, 1,000 kilohertz on your radio dial, which is like 1 megahertz, you know, in the center of your dial. So very low frequency compared to microwave, which might be in the 3 to 30 gigahertz. So it's way up there in frequency. And because of that, the antennas are very small. They're so small that you can take the radio energy and put it in a waveguide, which is a metal tunnel. And you take that waveguide with that very high frequency energy and let the energy come out of the waveguide at the focal point of a parabolic shaped antenna or reflector. The parabolic shape says that by definition the shape of the parabolic curve is such that at the focal point any line drawn to the curve would come out as a parallel line. So if energy hit here, it's going to go this way. If it hit here, it's going to go this way. You shape this curve so that this focal point energy reflects off in a parallel beam, okay? So we put the antenna right there at the focal point, and all the energy coming out of the radio gets shoved as a beam this direction. And then the theory of reciprocity works. Any energy that hits that reflector gets pushed to the focal point. That's where you have the receive antenna, and then the energy goes into the microwave waveguide into the radio. So you're communicating line of sight. This allows you to have up to about 3,000 voice channels, high-speed data. You can do quite a few things with microwave. The difference between a parabolic shape and a paraboloid shape, the paraboloid shape, like in this drawing here, has the focal point down below. So the focal point's on the bottom. It's almost like a mirror sending out a beam. And this is the same scheme as like in a satellite and a dish antenna for satellite. You've got that feed horn. That feed horn, the energy coming from the satellite reflects into the focal point, and that's where you pick up the signal. The same is true like in a football game. When you're watching on the sideline, you see a parabolic shape antenna looking thing, and at the focal point, that's where you put the microphone. And you can take that parabolic shape and you can point it at the quarterback, and they could talk very softly, and yet it's amplified into the microphone and you can hear what they're saying. So you see those parabolic shaped antennas all over the place. It's just a theory of reflection, and it works great. Microwave is very popular. There's analog and digital versions of it. It used to be all analog, very fast resync times. Digital with fast resync times on digital. There used to be an issue with it takes too long to sync up digital microwave, so we can't use it on power systems. But newer microwave digital systems are in use today because resync time after a microwave outage is fast enough to be able to use in protective relaying. So there's, you know, you're using microwave for the voice and the data, the protective relaying, the SCADA, you know, call centers, you know, company information, and those types of things. So that's microwave. Okay, the next system to talk about is fiber optics. Here we're talking about an even higher frequency. When we went from power line carrier, which was 300 kilohertz, to microwave, which was like 30 gigahertz, and now we're talking about 300 terahertz. we're getting up into the wavelengths of light, which is very, very small wavelengths. So small that the antenna really only needs to be a micron, a millionth of a meter, a micron. And then we're sending this very high frequency, very small wavelength energy through glass that's only a core that's only 8 microns in diameter. And the energy is reflecting off that core from the cladding, which is a different form of glass on the outside. And when you take this information and you put it through the core of a fiber and let the energy reflect, just like skimming rocks on the surface of a lake, if you can take that high density water and a low density air that's causing skipping and you can put it into a circle, and then you keep all that bouncing inside. That's what you're doing with light energy. You have a light on this side and it's blinking, and the light is reflecting through the core, bouncing off the cladding around the core, and at the other end you get light pulses. And then you have a photodetector on this side that converts the optical pulse to electrical signals. So you start with electrical signals, you convert to optical, the optical goes through the fiber optics glass, fiber. At the other end, the light's coming out. You put a photodetector there and convert the energy back to the ones and zeros again. So basically, you're going electronic to optical, optical back to electronic. You're communicating. The nice thing about it is one strand of fiber. There's this tube right here actually has 12 strands of fiber in it. One strand, the thickness of your hair, can handle millions of voice conversations at one time. We don't load up that much communications on one fiber strand because of putting all your eggs in one basket kind of scenario, but it's definitely capable of doing that. And the fiber optics is immune to electromagnetic interference, so you can use it in a lot of different areas. So this happens to be some static wire. This is the static wire, little band there to keep it from opening up all its strands. And inside are tubes of 12 fibers. And you can have 96 and even more fibers in one static wire on a transmission line. And our transmission system all over America is loaded with fiber optics. We have so much fiber optics in the static wire. And that's referred to as OPGW, optical ground wire. Here's a case where the static wire is coming down here. Okay, extra static wire is coiled around in case you wanted to cut it back for maintenance or move this fiber to another pole or something. And here's a splice case. So the fiber from the control building, which is plastic, it's all dielectric, comes in here, splices to the OPGW, and that junction box there allows us to have fiber optics inside the control building, okay, and out on the lines, okay? So when we compare fiber optics bandwidth for microwave or power line carrier or radio or anything else, fiber optics has much greater bandwidth. You can do video and all kinds of things with fiber. It's almost unlimited bandwidth. I mean, it's hard to even use it to its full extent. We use it extensively in the power system, for many different things. Even in transformers for sensors, fiber optics is used because of its immunity to electromagnetic and conduction. So that's fiber optic communications. Very important communication systems in the power industry. And just to talk a little bit more on the fiber, here's the core that I was talking about here, the core. You put energy within the aperture angle, so whatever light energy, if you have a flashlight or something, whatever energy you can get into that core, that energy will propagate through. If you bend the fiber too much, it bounces out. It's almost like throwing the rock into the water instead of skimming because you bent it too tight. Okay, you can lose it, almost like watering a hose. But then eventually the light comes out, and then you put a photodetector there. The interesting thing about here is when you have a pulse that's on for a very short period of time, because of the delay and the path that 1 micron signal in an 8 micron hole. Comes out with some dispersion, so you limit to speeds, and there's a lot of different things you could talk about in fiber. Here's a splice case mounted on a tower, and fiber optics, again, is very popular in the power industry because of its almost unlimited capabilities. Okay, to summarize up this module in telecommunications, we talked about the different types of telecommunication systems used in electric power, the fiber, the microwave, the power line carrier, etc. There are others like radio and what have you, but these are the primary ones that are used in protection and SCADA and those types of things. We described how the different telecommunication systems communicate data on both ends. We talked about 1,200 baud power line carrier all the way up to 6 million voice channels capability on fiber. You can put, on the fiber you could put different colors signals in, and the more different colors you use, blinking lights, the more communications you could put through the fiber. I mean, it's almost unlimited. Okay, so we talked about the different types of communication systems and power systems. I think it's good to know that this is out there. This is what ties the RTUs to the system control center. When you're in a system control center and you're trying to operate the power grid, it's through these communication systems that give you that capability. If you lose that communication system, you lost control, remote control of that system. And that's why telecommunications is very important in the power system.